Now, the next speaker, I'm really happy to have him here. I had a preferred speaker to have Snare here, and there's a lot of different topics he can be talking about. But the interesting thing is, you guys remember all the DMA stuff a couple years ago, the Firewire stuff. And he's been looking further into this, and that's really interesting. So I'm really happy, and we're gonna not waste too much time and just get this up and running right now. So everybody, Snare.
Thank you very much. So yeah, I'm going to talk a little bit about Thunderbolt, DMA attacks over Thunderbolt, sort of the evolution of the Firewire DMA attacks, and you know what my pal Resin and I did with some Thunderbolt stuff. So my name's Snare, or Lucas. I work at Azimuth Security in Australia. We do some computer stuff, apparently. Yeah, like the research I've done over the last few years has mostly been focused on macOS, like kernel and firmware stuff, so lots of UEFI, bootkit sort of persistence, bits and pieces, which has been a lot of fun, and then more recently, some more Thunderbolt related stuff. My buddy Resin, who couldn't make it because he's a grown-up and is finishing his PhD thesis at the moment and couldn't drag himself away, so he's in New Zealand, like typing on a keyboard probably. He's a PhD student, and he does like crazy FPGA stuff that I have no idea about with ray tracing and whatnot. So he did some really cool work on this as well. So yeah, so basically apparently Thunderbolt DMA attacks are a thing. People have been talking about it sort of since Thunderbolt became, you know, commonplace on Apple hardware. But like I hadn't really seen a proof of concept of this type of attack yet. I mean, you know, the only proof of concept had really been the Inception thing with a Firewire adapter. It sounded like a lot of fun. You know, I'm not a really smart hardware guy, so it was kind of a new area for me. So it seemed like something interesting to look at. And the talk title is slightly misleading. It's actually not about Lightning at all. It's just about Thunderbolt. So yeah, Stefan Esser was most unimpressed with that, but he's mostly just unimpressed all the time. So yeah, this is kind of the basic outline of the stuff that I'm going to be talking about. So I'll go through some of the background for Firewire DMA attacks, the way that they've been carried out in the past, and a bit of the history of the development of those kinds of attacks. A bit of the sort of guts of how Thunderbolt works, and you know, to contribute to that, how PCI works, and then a little bit about FPGAs, because that's kind of what the platform that we used to build this attack, and then how all of those things add together to form a Thunderbolt DMA attack. And I didn't bring my kit for the stunt hack demo because I've been traveling for like 6 weeks and didn't want to carry this big Pelican case with all the gear in it halfway around the world. But I do have a video of said attack. And then finally, I guess we'll talk about defense, because some people care about that. So I don't really. Firewire DMA has been around for quite a while. I think the very first instance of it that I've seen was this crazy guy at Apple called Quinn the Eskimo, who you might answer your really arcane kernel-related DTS tickets if you submit like developer technical support tickets at Apple. He's been there forever and knows all the inside of the kernel stuff. So he did this thing in 2002 where he like drew a screensaver on another machine by connecting the two things together via Firewire, and using Firewire SBP2 to like draw directly into the frame buffer on the remote machine using DMA. He didn't even think about doing a security, like he talked about the security implications of it, but at the time he was just like, this is cool, right? I can draw on the frame buffer on the remote machine over Firewire. Wow. And then a couple of people like Metalstorm, my buddy from New Zealand, went and took that idea and went, well, okay, we can write to memory, so let's maybe we can find some code in memory that's useful and change it so it's more useful, like the authentication routine that is called when you type your password into the Windows login screen. So he did this thing called winlockpwn that enabled you to basically plug in and overwrite some code and then log into the machine with any password. So that's basically what became Inception today. I mean, it wasn't that code, but like I think Inception's based on the same library that Metalstorm wrote originally in Python or whatever, lib 3094 or whatever. Yeah, so basically it works by, there's this sub-protocol or section of the FireWire spec called SBP2, which allows you to send a packet from one FireWire device to another FireWire device that says, please do a DMA read in system memory at this address. So we can, or a write, so we can, do sort of PCI Express DMA operations over Thunderbolt and then just spit the data out the Thunderbolt, the FireWire interface. Sorry, I keep saying Thunderbolt and I mean FireWire. So this is kind of what it looks like. We've got the target host there with a FireWire chipset, and then we've got the analysis host or the attacker or whatever you want to call it, depending on the context. You might be doing memory acquisition for forensic analysis or something, if you're not doing something actually bad. It's connected there via FireWire, so we've got two, FireWire chipset at each end. Analysis host says, bro, please read the data at this memory address. FireWire chipset sends a DMA read packet, or could be a write, depending on what you're doing, into system memory, and then sends the data back out the FireWire interface there to the other end. So there are some limitations of this attack, which have become more and more relevant in the last sort of few years, I guess. For starters, it requires that there be a FireWire interface on your machine. Practically nothing has that these days. I mean, it's pretty rare to find a machine with FireWire. Well, actually, maybe I have no idea. I mostly use Macs, so not much has FireWire these days, right? A limitation that's actually becoming more and more painful is the fact that that FireWire uses 32-bit addressing, so you can only actually address the lower 4 gigabytes of memory. I think there are some tricks where you can do some windowing stuff and get access to other memory, but it's a bit of a pain in the ass, right? So I haven't seen anything that actually does that yet. And finally, OS X, as a mitigation for this, the FireWire chipset driver actually, when you lock the screen, if you have FireVault enabled, which it considers your machine to be, you want some security features going on here, right? Because you've got full disk encryption. And if you don't have full disk encryption, then there's way easier ways to own your machine than DMA attacks, right? So, yeah, so if FireVault is turned on and the screen is locked, the IO FireWire family driver has a little bit of code that says, well, okay, let's set secure mode, and it tells the FireWire chipset to not do DMA anymore. So from that point on, the FireWire chipset just won't honor any SBP2 DMA requests until it's unlocked again. So that makes it kind of difficult to carry out these attacks in the scenario of person has their machine powered on with the screen locked, sitting on their desk, or asleep in their hotel room, and you want to wake it up and do something bad to it. You can't because of that mitigation, just regardless of the RAM limitations or whatever. So that kind of sucks. So Thunderbolt, I guess, is the next evolution of that. This kind of attack. So the way that Thunderbolt DMA attacks have been done thus far is basically just, we'll connect a FireWire chipset to the Thunderbolt port and then do FireWire again. So that's basically how most Inception stuff works over Thunderbolt. All Inception stuff works over Thunderbolt these days. So because Thunderbolt exposes PCI Express, which I'll go into in more detail shortly, you can basically just connect a FireWire chipset to the PCI Express bus over Thunderbolt, and then you have a FireWire interface. And because the Mac's already got a driver for the common Oxford chipset or whatever it's called for FireWire, it'll just load its driver and everything will work. So because it's basically the same as having an onboard FireWire chipset, you're limited to the same limitations apply as those that apply to an onboard FireWire chipset. So you still can only read the lower 4 gig of memory, blah, 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 blah. So that's Thunderbolt DMA thus far. So I'm now going to take a bit of a tangent and talk a little bit about how Thunderbolt works, vaguely. So Thunderbolt is basically just PCI Express and DisplayPort and some GPIO lines all glued together with some pixie dust and put over a 10 or 20 gigabit serial connection that's magic Intel technology. If you look closely there, you can see the pixie dust in the middle there. That's the Intel secret magic. So it's PCI Express. So we figure okay, well, we can probably send some DMA requests directly over Thunderbolt, right? So Here's a slightly more useful diagram of that whole rig, rather than the marketing one from Intel. So we've got the top there. You've got the processor and the platform controller hub connected to the PCI Express bus and DisplayPort and whatnot. So we've got 4 lanes of PCI Express going out of the PCH into the Thunderbolt controller, which might be one of the Intel ones, like a DSL 2210 is a common one. And then we've got DisplayPort coming out of the PCH or out of discrete graphics hardware. You can see on this side of the diagram there, which I didn't point out, or going into the Thunderbolt controller. And then we've got this 10 or 20 gigabit full duplex serial link between the two hosts, or between the host. In this case, it'll probably be a host and an endpoint device like a Thunderbolt hard disk or something, right? And then at the device end, we've got another Thunderbolt controller, like a DSL 2210 again, which splits out the DisplayPort, PCI Express, whatever. And then if you say it's a Thunderbolt hard disk, you'll have a SATA controller, a PCI Express SATA controller connected to the PCI Express coming out of the bottom of that Thunderbolt controller there. So essentially it's the same as having, a couple lanes of PCI Express coming out of your PCH, and then you've got a SATA controller chip on board connected directly to PCI Express with a few sort of caveats, but that's generally the gist of it. So inside the Thunderbolt controller, we've got something that looks kind of like this. This is from Apple's programming for developing Thunderbolt devices or whatever documentation. Most of the documentation, it's very difficult to get. This is the only public document from Apple about Thunderbolt, which is in the references if you want to have a look at it. But like Intel, I tried to register for the Intel Thunderbolt developer program, and they were like crickets. And I tried again, and they were like, yes. So like 2 weeks later, someone sent me an email saying, yeah, we'll get back to you in the next 2 to 3 months. And of course, crickets. I heard nothing. And then I went and spoke at their developer conference about UEFI a couple of years ago, and I asked all the people, can I please, have some like Thunderbolt developer stuff? And they're like, no, just that's not going to happen. So yeah, they're pretty closed-mouthed about the internal documentation about that stuff. So yeah, so basically the guts of the Thunderbolt controller looks like as you would expect. You've got your PCI switch and your Thunderbolt switch. And you've got DisplayPort coming in at the top there. PCI Express comes into the PCI Express switch, and then it goes out into the Thunderbolt switch, which does all its magic serializing, like serial stuff. And then you have it connected to the Thunderbolt switch at the other end, and then it comes out. So we have PCI Express going in here, and then going into the Thunderbolt switch, coming out of the Thunderbolt switch at the other side, and then coming out of the PCI switch at the other side, PCI Express switch at the other side. So, conceptually, it's not that complicated, but unfortunately, none of the chips, it's impossible to get data sheets for all the chips because, again, they're like, no, you have to be Belkin and be selling 1 million devices or whatever in order to get the doco. Jerks. So, now I'll dive into PCI Express a little bit because that's probably pretty relevant for how all the shit works. So, this is like Sam's stuff that I have no idea about. A lot of it, but PCIe is like sort of the evolution of PCI and PCIX, but it's not also like PCI. Had this sort of everything's connected to the same bus topology, and PCI Express is everything's point to point. So it's this like fast, high speed serial point to point interconnect thing with a scalable number of lanes that are negotiated at link setup. So a lane is just like a unit of throughput, basically. So, you have like a single lane, 2 lane, 4 lane, 16 lane card in your computer. Your big fat graphics card for mining Dogecoin or whatever is like 16 lanes, and it's the number of lanes is negotiated at link setup. So you can have a 16 lane card, and it'll just use 1 lane if that's all that's available. So say there's an electrical fault that results in 1 lane being broken, or you've like sawn the end out of your 1x slot and jammed a 16x card in there, it'll still work, but it'll just negotiate at 1x, right? So yeah, so it's pretty like it's actually pretty simple, electrically, because there's only 4 wires per lane, so there's 2 differential pairs, so it uses differential signaling to like mitigate noise the same way that the microphone cable does with a balance cable, two out-of-phase signals and then add them together at the end, or whatever, subtract them at the end, I don't know, and you don't have any noise. So from sort of above the electrical layer, it's a layered packet-based transaction protocol. You know, it's actually kind of similar to, you know, a lot of networking protocols in that regard. There's a physical layer, you know, with the electrical communications, a data link layer and a transaction layer. Really all we're concerned with for DMA stuff is the transaction layer. So we send like TLPs or transaction layer packets from our endpoint device to do DMA stuff. So that's kind of what the stack looks like, I guess. You've got your transaction layer at the top, data link layer, physical layer. TLPs, you know, go start at one transaction layer and finish at the other transaction layer, and they're, you know, connected in the middle. They're electrically by those two differential pairs. And this is kind of what the network topology of a PCI Express, you know, setup in a standard host would look like. You've got your CPU. You can have multiple CPUs, and that complicates things a little bit because you can only have one that's the sort of master of the root complex. But so assuming a single piece, CPU system, we've got the root complex, which is sort of, you know, the main brains of what everything else connects to. You might have a PCIe switch like, you know, the little blue guy there. I think I stole this from an Intel presentation like everyone else does, this diagram. And then off the PCIe switch, you might have, you know, a bunch of other devices. You can also have a legacy device that uses, you know, I/O reads and writes rather than, you know, DMA stuff and message signals, interrupts, and all that kind of junk. That, you know, you might also have a PCIe to PCI or PCIX bridge to connect, you know, real legacy devices. So if you've got a, you know, typical desktop motherboard these days will probably have, you know, maybe one PCI slot or one PCIX slot, then a whole bunch of PCI Express slots. Well, a whole bunch of PCIe 1-lane slots, maybe an 8-lane or a 4-lane and a 16, or maybe two 16s if it's like a super gamer nerd system or whatever. And then, importantly, you've got the memory also connected to the root complex there. So transactions in PCI Express, we've got 4 transaction types. There's only one that we're particularly concerned with for this piece of work, but there's I/O reads and writes, which are kind of deprecated now. Like they still work and they're still part of the spec, but most devices don't use them. Most devices use memory mapped I/O stuff. You've got configuration reads and writes, which is for reading and writing to the configuration registers on the device for configuring it and determining what its configuration is. Memory reads and writes, which is the ones that we have a lot of fun with. And then we've got messaging, which is like for signaling interrupts, because PCI Express does, I mean, it supports level sensitive interrupts on, you know, pins on the CPU or whatever, or on the PCH. But most interrupts driving stuff now is done just by message signal interrupts. So you build like a little MSI packet and you write it to a specific address with a DMA write command, and then that becomes an interrupt in the APIC. So DMA, well, like the busmaster thing is kind of sort of redundant now, but it's still necessary. In PCI or PCIX, a device was granted busmaster. Because of the way that the topology worked, only one device could sensibly be the busmaster at a time and be able to do, you know, DMA reads and writes on the PCI bus. But that's not really a thing with PCIe, but it's still enforced that way because they wanted it to look kind of like PCI. So busmaster, you know, we need to get something to configure the device and tell it that it's the busmaster, and then it can, from that point, send TLPs, direct memory access, DMA TLPs, to the root complex and tell it to do reads and writes or whatever. So when we get busmaster, we just like, you know, from software, if we wanted to give a device busmaster and do a DMA thing, we can just like, so like a legitimate DMA operation, say a graphics card, you know, tell it, you upload a kernel thing to the graphics card and say, do all this stuff, and then when you've got a big bitmap of the image that you've rendered, write it back to this, you know, address or something. So you write the target address and the command to the device, it does the thing, and then it signals an interrupt when it's done. So, yay. So these are all the, like this is actually from an Intel document, again, table of all the request types that we can send. It's basically what I just said, but with all the, official names for them and stuff. So the important ones are like MWR for memory write and MRD for memory read. The completion ones we have to deal with as well because that's what the device will send when it's like done, whatever you asked it to do. So FPGA stuff, who knows what an FPGA is? Most people. That's good. So for those who don't, an FPGA is basically a reprogrammable IC. Like it's a chip that you can do things like lots of other chips. So an IC is built of different logic blocks that do things connected together in a specific way, right? So an FPGA is just a matrix of configurable logic blocks that can each one of those logic blocks can do the job of any other type of gate, depending on its configuration. So we can build lots of different types of circuits out of an FPGA just by writing, some code to configure it. Yeah, there's a bunch of other stuff there, but the important ones, I guess, are the device-specific features of the FPGA that we used. It has a hardware PCI Express, a PHY block for actually doing the electrical side of PCI Express, because we used the cheapest possible FPGA we could get that supported PCI Express, and it only runs at 100 megahertz or whatever, and it's not fast enough to actually do the signaling on the PCI Express bus. So it has a hardware like transceiver, PCIe transceiver, as part of the FPGA. Yeah, so that's a diagram that represents what a lookup table is. A LUT or a lookup table is just one of those little logic blocks that could represent any other type of gate. So one of the other features of Xilinx FPGA that we used, or one of the things that you get for free with their software, is a virtual microcontroller architecture called MicroBlaze. So it's basically this, very similar to an AVR or whatever whatever your favorite microcontroller architecture is. They're all quite similar in their implementation. It can also interface with an AXI bus. AXI is kind of like the ARM version or microcontroller version of PCI Express. So it's just an interconnect bus for use on die within system of modules and stuff like that. So all of your phones probably have an AXI bus that's used to communicate between the CPU and the Wi-Fi card and shit like that. Although a lot of the Wi-Fi cards use SDIO as well. Yeah, so AXI is very convenient for us in this case because lots of off-the-shelf IP cores, which are just like chunks of logic, of FPGA logic that other people have already developed that you can just license or borrow, whatever. So lots of them talk AXI, lots of them talk Wishbone and various other interconnect sort of formats, but AXI is quite convenient because all the Xilinx stuff pretty much talks AXI. So MicroBlaze, like this, how many people have done any FPGA development here? Okay, so a few. So for everyone else, don't. It's hard and it's really annoying, right? Unless you're an engineer. From a software guy's perspective, it's a real pain in the ass. And debugging stuff is really difficult. I shouldn't say don't. It's heaps of fun as well, but it's frustrating. So debugging stuff, debugging issues with your logic is, you inject like a logic analyzer core, and then you talk to it with this chipscope logic analyzer program or whatever platform you're using, and you just get like lines out of it, which is kind of makes debugging tricky. So for me, I really liked MicroBlaze because I'm like, cool, I can write C code now and I can debug it with like a debugger that looks kind of like GDB, and everything, the world all makes sense now again. So you write code in C or C++, compile it with the XSDK, and just upload it to the virtual microcontroller running on the FPGA. So we're basically using it here for writing control logic, like stuff to tell the PCI Express block in our FPGA design what to do. Otherwise you have to write a state machine in VHDL or Verilog, which is time consuming for it's relatively time consuming for things that should be, pretty simple, and to write a little, loop in C to do some shit. You got to write this big state machine in an HDL, and then it's very difficult to debug. So yeah, and it also means noobs like me can write code for it, which is great. So I don't have to rely on Sam to do his chip scope magic and look at the, square wave output and go, yes, that's a completion packet with an error, while I go, what? So one of the other neat features is we've also, it's got a serial, we've got a UART on the development board, and can communicate with the microblaze code via serial. So we can, I wrote a little, text UI thing, and we can just connect to it via serial and send some commands, and our code then tells the PCI Express block what to do. Great. So yeah, AXI PCI core. We've got this piece of IP that comes with the development kit that you can use to interface with the PCI Express physical transceiver from AXI or via AXI, and then we can do the AXI buses. The AXI bridge, AXI to PCIe bridge is memory mapped into the microblaze's memory space, and then we can just do memory reads and writes into the AXI core, and then they get translated into PCI Express transaction layer packets and just get sent out the PCI Express bus. So it basically means that it's pretty easy for us to do arbitrary PCI Express TLPs from our microblaze controller written in C. So it's nice. Okay, so that's all well and good. We can talk PCI Express out our FPGA now. So how do we actually talk Thunderbolt? So this is the board that I bought to talk Thunderbolt. It's a B+ TH05. It's basically just a single PCI Express 1X slot, and then a Thunderbolt chipset, which is like a DSL 2210, which is a common Intel Thunderbolt chipset that you'll find in, your Thunderbolt hard drives and stuff like that. So it actually got discontinued. This is I got an engineering sample of this thing, and they had a whole bunch of products on their website that were Thunderbolt things. Excuse me. And so I got an email from them saying, hey, we've discontinued this and we're recalling the whole line. And I was like, well, no, I need this for my research project. And they were like, no, send it back. We'll give you your money back, and we'll pay for postage and everything. And I was like, no, what's wrong with it? I need it. And they were like, what? No, we can't really talk about it, but just send it back. We'll give you your money back. We'll pay for the postage. We'll give you $500 worth of credit on our web store and a free T-shirt. I'm like, well, okay. So you really want this thing back, huh? No. And then I think it's actually the reason that my Thunderbolt port on this machine doesn't work anymore. But yeah, so after that, all of the devices that they had that were Thunderbolt products disappeared from their web store and have never returned. They scrubbed everything that they could possibly find off their website. And I emailed the guy that I know at Intel, and I was like, hey, so B+, huh? And he's like, yeah, we're not going to talk about them. So I suspect, either Intel was suing them for building Thunderbolt devices without being licensed, or they were undergoing certification, and Intel went, certification to be able to actually build Thunderbolt devices and sell them, and then Intel went, like, you got to remove all this stuff, and then nothing happened. So anyway, that was quite an interesting device. So we've now got our, I don't think I even mentioned before, the Xilinx SB605 is the development board that we use. So that's got, I'll show you a photo of it in a sec, point out all the bits. But it's got our, FPGA on it, and it's got a PCI Express finger hanging out of the side of the FPGA. It's because it's most of the boards that are built by FPGA manufacturers with PCI Express are basically designed for building new networking hardware. So they have every feature under the sun, and most of them are really expensive. They'll have an SFP slot, a gigabit Ethernet, DVI, HDMI, a big FMC mezzanine connector to connect thousands of pins to everything else. All this, lots of hardware, hardware debugging stuff that I have no idea about. But yeah, basically it's a giant board, and they're really expensive. Actually this one's very cheap, but most of them are very expensive. So there's circuitry on the board and within the FPGA itself that handles the PCI Express physical layer electrical stuff. So that's that block in the FPGA that I mentioned before that does the transceiver stuff for us. Some of the higher end FPGAs that run at a higher clock speed and have a fuck ton of logic, you can actually implement the whole PCI Express transceiver on the FPGA. So we've got our AXI to PCI Express core there that talks to the microblaze, and then we just do our memory reads and writes into the AXI core, and it does the PCI Express stuff. All goes out the Thunderbolt connector to the target host. And then we've got our analysis host there, or attack machine, that's just connected via serial. It doesn't really need to be there. Like, we've built a thing so you can just like press a button on the FPGA board and it'll do all the stuff. But just for debugging purposes, we connect to it via serial and JTAG, so we can do neat debugging. So yeah, this is basically what it looks like. So similar to the old the FireWire diagram from before. So we've basically got the two Thunderbolt chipsets there connected via a Thunderbolt cable, but this time the PCI Express bus is extended right outside the case and into the analysis device through the Thunderbolt chipset, and then we've got our FPGA connected to it at the other side. So yeah, with a few caveats, it's essentially the same as having it connected directly to the PCI Express bus. So our FPGA goes, dude, do a DMA read, and sends a TLP straight out the Thunderbolt interface to the memory and comes back with the data. Okay, so actually attacking an operating system over PCI Express and over Thunderbolt. So we first of all we wrote our own driver. Just to get the development side of this done, we wrote our own driver that we load on our target machine to cheat and talk to the FPGA via PCI Express to configure it and tell it to do some stuff. This is before we had the microblaze design done. We had just a state machine that told the PCI Express thing what to do. So we just write to it over PCI Express, and say, write to a register that says do a DMA read at this address, and then put the result into this register, and then we'd read it back from our driver again and go, hey, cool, it worked, or no, it didn't work. Let's do all this debugging stuff in chipscope. So the second phase of that, what's going on there? Okay. The second phase was to basically imitate another device. So when we plug our FPGA into the Mac via Thunderbolt, we imitate a device that it knows about, a PCI Express device that it knows about, so that it loads a driver in the OS. And then that driver can configure busmaster and set up, ACS and whatever other requirements we have for the system to be prepared for us to poke at its memory. So back to PCI Express, a little bit about the way that this configuration space stuff works. So you're probably familiar with config space if you've done debugging of PCI devices like graphics cards and stuff, trying to get them to work, and working out why why it's suddenly writing to a DMA buffer that's like shitting all over your kernel text or something like that. So basically, config space is just a little chunk of data that's presented by the PCI Express device, which has a whole bunch of properties in it that describe the configuration state of the PCI device. So you can read and write to config space. Some fields you can only read, and some are only useful to write to, but you can also read back from them because they're there. But the important ones for us are like vendor and device IDs. So there's like, a vendor number like 8086 in hex for Intel, and other, you can go look up those, a whole table of them on the internet. And the device ID is just an ID assigned by that vendor that represents what that specific device is. So that's up to them. And there's also some other things like there's a class code and a subsystem ID and class revision ID and subsystem vendor ID for representing multiple devices on one device and stuff like that. There's register base addresses that specify base address registers. I don't know why I wrote that. That specify the base address for a DMA buffer that the system can just write stuff into, or or a set of registers that are protocol specific. So say a SATA adapter will have a set of registers that which one to write to based on the SATA spec or whatever. Um, yeah, so that's kind of what it sort of looks like. The important ones that I mentioned: device and vendor ID, class code and revision ID. So a class code, you might say, well, this is a common SATA device. So there's a spec that, specifies how to communicate with this type of device regardless of who the vendor is. So it's just a common type of device. So you can have a class code and then a revision ID for different versions of that protocol or that specification. Yeah, subsystem vendor ID, so the base address registers there. And then the other fun one is the expansion ROM base address. So if the device has an expansion ROM, then it'll have an address in this field, or you set 1 bit in that field, and then it writes the address to that field, and you can read it back. And then you can, when the device is connected, the system, at boot time, the system will read that register and go, oh, cool, there's an expansion ROM. I have no idea how to talk to this device, but there's a driver on it that's going to tell me how to talk to it. So it'll just load the driver off that device and into the BIOS, which I had a lot of fun with UEFI, because it means if you connect a device at boot time, like a Thunderbolt to Ethernet adapter, with an option ROM that you've written yourself that does something that's not actually tell the system how to interface with the hardware, oh, I don't know, inject a payload into the kernel or something, then yeah, that can be a lot of fun as well. Yeah, so capabilities as well, whatever. Okay, so IOKit. So IOKit is basically the thing that manages all the drivers in the macOS kernel. There's a couple of other driver interfaces, but IOKit's the primary one, and it's the one that automatically loads drivers when stuff gets connected or whatever. So when a new device is connected to a running OS X system, all the drivers in the system all the IOKit drivers in the system are searched to find a match for the device that was connected. So it'll look at if you have an IOKit personality in your driver that says this driver is for devices with this vendor ID and this device ID, or it might say, as I said before, this class code and this revision ID, or this class code and all revision IDs. You can have masks for it, so you can say all revision IDs, that start with this bit, or that have these bits set and none of these bits or whatever. Or you could say this driver is for every single device ever manufactured by this vendor or whatever. And there's also a name which is generated by the vendor ID and product ID, and there's some other criteria, if some other things exist, they'll be used to generate the name. So that's the one that we used. So in this instance, this is actually from the documentation, the IOKit driver matching documentation. So you can see there in the IOKit personality, there's an IOPCI match field which has just a number containing the entire vendor ID and device ID just stuck together there. So that's one way of matching. So this is the device driver that we actually targeted to pretend that we were its device, which is the Apple SDXC slot. So on a MacBook Pro, it's got a secure digital SD card slot on the side, so that the slot, the reader, has it talks to this driver. So this is the IOKit personality that we emulated. So we set our device ID and vendor ID to 14E4 16BC, like that, which is used to generate the name, the IOKit name of the device. And so if we had the same vendor ID and product ID, then this driver will get loaded when we connect that device. It won't know how to talk to us because we're not actually an SDXC slot, but it will do things like set bus master in our config space and stuff like that. So this is one of the caveats that I mentioned before about devices that are connected over Thunderbolt. So there's this IOPCI tunnel compatible flag. So if the device is connected via a Thunderbolt bridge, and the IOPCI tunnel compatible flag is not set in the driver, or set to no, or doesn't exist, then this driver won't be loaded for something connected over Thunderbolt. So we had to just find a driver that was, had IOPCI tunnel compatible, and there's 15 or 20 of them, I think, including this one. Right, so the proof of concept thing that we built is basically the same as Winlock, Pwn, and Inception. So we find the code that does the authentication lookup. So when the screen's locked, you type in your passphrase. It goes and looks it up against the system's database thingy, open directory. and returns yay or nay based on what you typed in, right? So we find the code that actually checks that, and then using a DMA write request, a MWR TLP, we just overwrite that little bit of code with, you can see it there. It's move B into A, which is just the result of the actual. Sorry, move A into B. Yeah, whatever. I can't remember how that code works anyway. It basically moves the result of the I can't remember if that's Intel syntax or AT&T syntax, because anyway, it's from IDA Pro. But yeah, we're moving B into A. So I'm not sure how B gets set, but it's basically the result of the calling that OD record verify password function, which goes into Open Directory, looks up the password that you typed in, and whatever. So we just override that with a move 1 into AX. So the function will just always return 1 then. So this is our demo, this is our board that we use for this proof of concept. So that's the FPGA development board there. There's the FPGA, that nasty looking BGA package there. And there's the Thunderbolt to PCI Express board, that B plus TH05. And I mean, now you can get this, I bought this a long time ago, and now you can get there's lots of Thunderbolt enclosures that you can buy from Magma and from Sonnet and whatever, that just have a PCI Express slot in a big enclosure with a power supply, which is, basically for having external graphics cards, that video capture cards that you plug into your laptop if you're a video professional or whatever. So there's the PCIe finger in the 1X slot there. Then that's the Thunderbolt connector with the black Thunderbolt cable plugged into it. So this is the whole sort of setup. We've got our attack machine there on the left with the JTAG and UART connected to us, so we can do our debugging and see the serial console output from the FPGA. And then on the other side, we've got the Thunderbolt connected to the victim machine there, which is this machine. And then we've got the hairiest alpaca in the world there as well, just for reference. So, in case that didn't make sense, hopefully this will actually volume. Nope, hang on. How do I even sound? Sound doesn't work. Oh, there it goes. I suck. I don't know how to computer anymore.
Okay. First, I'll access a secret military spy satellite that's in a geosynchronous orbit over the Midwest. Then, I'll ID the limo by the vanity plate Mr. Big and get its approximate position. Then, I'll reposition the transmitter dish in the remote truck to 17.32 degrees east. Hit West Star 4 over the Atlantic, bounce the signal down into the Azores, up to Comsat 6, beam it back to SATCOM 3 transmitter number 137, and down to the dish in the back of Mr. Big's limo. It's almost too easy.
So that's basically how our attack works. Yeah, and as I said, I didn't bring the kit because I didn't want to carry this big thing around the world. So I made a video, which doesn't require sound, of the attack taking place. So there's Sam pressing space and hitting enter and going, no authentication, this is no good. So we plug the Thunderbolt connector in there. See all the lights come on the Thunderbolt board. Give it a couple of seconds, and then we get our prompt on the serial console saying everything's okay. We type our unlock command, and then it goes off and starts searching through memory, finds that little bit of code that we're looking for, and patches it with a move 1 into AX, so that when we actually try to authenticate, it'll succeed. Just wait for it to finish because it has to search through all 8 gigs of memory in that machine. It's done. So we type space, hit enter, and it's unlocked. So we owned all the shit. And then there's a really surprised Otter there who's like, oh my god, you own my computer. Yeah. So yeah, that's the stun hack. So this seems, thanks. I love a good sun hack. So this seems kind of bad, right? Like, it doesn't seem like a thing that you should be able to do. Obviously, already didn't with Firewire, but there's been some mitigations for that. So yeah, Intel realized that this was probably not a good thing, I guess, especially when it's extended, you know, when you have the main system bus extended outside the case like that. I'm kind of running out of time, so I'll have to move through this kind of quickly, but it's only defensive stuff anyway, so who cares? So yeah, so they realized it wasn't a great idea. I mean, it's the same thing as having an express card, right? You can do exactly the same thing with an express card device. So, I mean, you wouldn't even need a Thunderbolt 2 express card. Like, you know, we wouldn't even need a Thunderbolt chipset involved. You can just like go from your PCI Express finger connected on the FPGA board with like through electrically straight through with a like a PCI Express to express card adapter, which is just a form factor change. Plug it into express card and off you go. So I guess the options are like, yeah, glue all the ports shut, which is obviously an option for some people, but not for most of us. Maybe a voodoo curse on Intel or something, but I'm not sure whether that would work. Or maybe apply some access controls to I/O, which is what they've gone and done. So they invented this thing called VTD, which is you know, primarily for virtualization. But it's also a bit of a security measure against this kind of attack, as long as it's configured properly, which it often isn't by the operating system. So VTD is basically this. We've got a set of traffic lights in there inside the platform controller hub that like, there's a little bit more to it than that. There's like remapping of DMA addressing so that, you know, you, anyway, it's virtualized I/O. So it's how VM direct path works. So you can basically take a device and map it directly into one of your virtualization guests. So if you've got, you know, 2 graphics cards and you've got 2 guests, then you want to assign the graphics cards directly into the guests, you can do that. And, you know, only that guest will have access to that graphics card. And the graphics card won't be able to read and write to the host, the virtualization, like VMM's memory, because VTD has like partitioned it and you know, assigned that device directly through to the guest there. So DMA requests are remapped with access controls, and interrupts are also remapped with access controls. Those two things are separate features of VTD that can be configured independently. So for example, Mac OS 10 configures DMA remapping, but it doesn't configure interrupt remapping. So, you know, there's slight difference in the way that that's configured to the way I think Linux actually does configure interrupt remapping, but it does a completely different and quite awful job. Not awful, but it's a bit messy job of its DMA remapping, request remapping. Although at least it uses different domains, which is something that OS 10 doesn't. So VTD has a set of domains, which is, you know, if you want to assign a device to a guest, you create a new domain for that guest, and you assign all those devices that you want to assign to the guest into that domain. So if you had 2 guests with 2 graphics cards, you have 3 domains, because you have a domain for the host as well. So there's always at least one domain, which is the host domain, and OS 10 just configures one single VTD domain, which is not a big problem security-wise, but it just means that you can't actually do like VM direct path style stuff without reconfiguring the VTD unit from the VMM, like from VMware or whatever, which is probably not a great idea. Because there's no support for the way that the VTD is configured by the OS. We had to go in and write use a modified kernel or a driver that like finds the VTD unit and pokes at it and reads all the registers and reconfigures it and stuff, and it's quite painful. So so the OS 10 kernel configures VTD for you automatically. Actually, the IOPCI family driver does it. All devices are in a single domain. So now when a driver allocates a DMA buffer, so say you've got a graphics card driver, it's going to allocate a buffer, a DMA buffer for the graphics card to write the results of some graphics stuff back into the main memory. When that buffer is allocated, the actual allocator, like the kernel allocator function for allocating memory from a driver, so for IOKit, automatically does the VTD setup and says, okay, well this device driver is for the device that belongs in this domain, so we'll assign, say that only this domain can access this device is the only thing that can access this DMA buffer, and that's it. So then, if your driver configures DMA buffers, so the SDXC driver configures some DMA buffers for us, so we can read and write those, but we can't read and write all of the other memory on newer machines that have VTD. I think I put these in the wrong order because this is the important part, where VTD is only on Ivy Bridge and later machines, so also on the new Haswell machines as well. But the machine that we tested on was the Sandy Bridge machine, because we did that video a little while ago. Yeah, so Windows 8, well, before 8 doesn't actually configure VTD at all. So on any Windows 7 machine, if you're running Windows 7 on a Mac with Thunderbolt, you could do DMA attacks over that, or Windows 7 on a machine with Express Card, you could do the attack over that quite easily. Linux, yeah, does separate things into domains properly, which is kind of neat, even when there's no virtual machine manager going in and saying I need different domains for different guests. So that's basically just a graphical representation of what I just said. So pre-Ivy Bridge on a pre-10.8.2 machine is ownable. Pre-Ivy Bridge on greater than 10.8.2 is ownable. So any pre-Ivy Bridge machine doesn't have VTD, right? An Ivy Bridge machine that does have VTD, if you're running an older operating system, it's still ownable because it doesn't configure VTD for you. But if you're running anything later than 10.8.2, which you probably are by now, then it's configuring VTD and you won't get owned. Yay. So some, kind of running out of time, but so that's basically, I think that's pretty much close to it. Basically the next steps for this research would be making the kit a little bit smaller, because obviously it's gigantic and unwieldy, and at the moment it requires 2 power supplies for the board, or one for the board and one for the Thunderbolt board. So we've worked on building a new board that's like bus powered and tiny and all integrated and stuff, but we haven't quite finished that yet, so it's sort of we're in the process of designing it at the moment. Bypass VTD, poked around with VTD a little bit. There's maybe some possibilities for telling it to fuck off and let us read memory. I'll also maybe see if we can do it without actually having to imitate a device and just say, we are bus master and we're going to do all the reads and the writes. But we didn't, explore that too far because it suddenly worked and we went, cool, I'm not going to touch it now because it works. Full memory capture, so like volatility analysis. So like actually reading the entirety of memory and dumping it out the gigabit Ethernet interface on the FPGA board, or maybe writing it to an SD card or something like that for later analysis. Payload injection, I guess, like find some kernel memory and override it with a malicious payload, or like do things like find the page tables. No, I guess find the allocators, data structures in kernel and like modify them and allocate yourself some memory somewhere, and then write your payload to a page that you've just allocated as part of kernel memory, and hook some kernel code to point to that, and then you win with a nice little kernel driver injection thingy, and also driver vulnerability exploitation. Like there's even if we can't read and write to main memory, we could emulate various different devices and then fuzz the shit out of their drivers. So we say, hey, I'm the J Micron SATA adapter or whatever. Talk to me, and then the driver gets loaded and it talks to you, and you send it back a response that it's not expecting and get code execution or something. So there's lots of possibilities like that. Joe Fitz did some cool research like this as well, and he built this slot screamer board, which is a PLX USB 3380 chipset, which is a PCI Express to USB 3 chip. And you can actually, as part of the USB 3 spec, you can talk to the chip over USB 3 and say, hey, do DMA reads for me and writes. But it only works on 32-bit. It only supports 32-bit PCI Express, so it can only do lower 4 gigs. So there's a few limitations on that, but it's a really cool board as well. It doesn't have Thunderbolt, so you still need an additional Thunderbolt enclosure or whatever. So yeah, that's pretty much it. There's some references, which I'll upload the slides if you want to actually get those references. And that's pretty much it.
All right.
So thanks very much for having me. Thanks to the SecT guys. It's been an awesome time so far.
Thanks for coming. But it's not very common that all the questions that I want to ask actually gets answered in the end of the talk. It's like
I was trying to do that.
now he's talking about these things that I want to ask. So when are you going to make this kit so small that you can buy one? Like, will you build one?
We're working on a board at the moment. May release it, may not. See what happens. Yeah, we're going to use like a different FPGA and a different hardware microcontroller and stuff. So yeah, it's in the works at the moment. So probably in the next few months it'll come to fruition, hopefully.
Right. What's the like the reaction from the vendors when you talk to them about this, or the manufacturers?
Honestly, meh. You know, we know, like, you know, Intel know that it's a thing. They've known for a long time that it's a thing. You know, that's why they invented BTD. I guess, like, there's still heaps of other attack vectors, like I sort of described at the end there. But they're basically like, yeah, we know. Apple's like, yeah, we know. There's things that they could do about it that they haven't done about it, that I've talked to them about, but yeah.
All right. Do you have questions from the audience?
Feel free to come and grab me later if you have questions that you don't want to yell out or whatever.
Exactly. Well, you're not disappearing, so you'll answer questions.
No, I'm happy to answer questions now as well. But, you know, if you have longer discussions, I'm happy to chat later on.
All right, in that case, you're probably wanting coffee or something. So thank you very much, Snare, for coming.
Thank you very much.